The last subtopic is 2.3 Applications. At the end of this lesson, students should be able to solve problems involving first-order differential equations. And we will learn a few applications including Newton's law of cooling, electric circuits population growth model, radioactive decay, and problem related to velocity and acceleration. So the first application is population growth model. The simplest growth model has a constant relative growth rate. The word rate here means it is related to time. If we denote the population by y of t, then the rate of change of the population is dy dt. To say that the rate of change is proportional to the population is just saying that there is a constant of proportionality k such that dy dt equal to ky. Okay? And from here, we have dy dt on the left, ky on the right. We have two terms only. So we can try to separate the variable. So we can write 1 over y dy equal to integrate k dt. By integrating both sides, we will get ln y equal to kt plus c. By taking exponent for both sides, we will get y equal to exponent kt plus c. And by using the rule of indices, we can write e kt times e c. And by letting exponent c as a, the equation becomes y equal to a exponent kt. Okay, now we go to the example. Okay, example number 6. In a particular bacterial culture, the rate of increase of the bacteria is proportional to the number of bacteria and present at time t hours after the experiment and follows the equation. Okay, given one equation here. Okay, and given that the number of bacteria at the beginning is 10 power of 6. So we can construct a table to write all the given information. So when t is 0, okay, the number of bacteria is 10 power of 6. Then, after 1 hour, t is 1. The number is 10 power of 9. Find the number of bacteria after 5 hours. So when t is 5, what is the population? Okay, so from the given equation, we can write dn over dt equal to k times n. So we try to separate. We have 1 over n dn equal to k dt. Next, we integrate both sides. We will get ln n equal to kt plus c. By taking exponent for both sides, we will get n equal to exponent kt plus c or equal to exponent kt times exponent c. Okay, and then we let exponent c as other letter. So let's say we use A. Therefore, we will get n equal to A exponent kt. So this is the general solution. Okay, now we will use all the given informations. So we have when t equal to 0, okay, your n is 10 power of 6. So we substitute into the general solution. So we will have 10 power of 6 equal to A exponent 0 times t. Sorry, 0 times k. And exponent 0 is 1. Therefore, we get A equal to 10 power of 6. Meaning that n equal to 10 power of 6 exponent kt. Okay, next information is when t equal to 1. So we substitute, okay, into the previous equation. So we have 10 power of 9 equal to 10 power of 6 exponent k times 1. And next, we will get exponent k equal to 10 power of 9 divided by 10 power of 6. We will get 1000. Therefore, k equal to ln 1000. And the equation becomes n equal to 10 power of 6 exponent ln 1000 times t. Or we can write as t ln 1000. So this is the equation. Next, back to the question. Okay, you need to find n when t equal to 5. Okay, so the question is when t equal to 5. So we substitute t into the equation. So we have n equal to 10 power of 6 exponent 5 times ln 1000. And you can use your calculator now. And we will get 10 power of 21. So the population is 10 power of 21 when t equal to 5. Now we go to part B. Find the time taken for the number of bacteria to be 3 times the original. Okay. So when t equal to 0, the initial, the original, your n equal to 10 power of 6. Okay. So 3 times the original, meaning that 3 times 10 power of 6. So this is the question. And now we substitute n into the equation. So we will get 3 times 10 power of 6 equal to 10 power of 6 exponent t ln 1000. Okay. So we have exponent t ln 1000 equal to 3. To eliminate ln here, we need to take ln for both sides. So by taking ln both sides, we have t ln 1000 equal to ln 3. And you can use your calculator now. You will get T equal to ln 3 over ln 1000 and equal to 0.159 hours. The next application is radioactive decay models. Radioactive decay models, on the other hand, are very accurate over long periods of time. Okay, if you refer the word here, we have word decay, meaning that the rate is decreasing rate. So that is why we need to write dc dt equal to negative k times c. Okay, and c is the amount present. Okay, so we have here dc over dt is negative k times c, and by separating the variables, we will get 1 over c dc equal to negative k dt. And by integrating both sides, we will get ln c equal to negative kt plus d. I'm using d here because I have c already. Okay, so we need to use the other letter. And then by taking exponent for both sides as usual, okay, so we will get c equal to exponent negative kt plus d, and we apply rule of index. We have exponent negative kt times exponent d, and we state exponent d as a, so we will get c equal to a exponent negative kt. Now, we go to the example. Radium decomposes at a rate which is proportional to the amount present at any time and follows the equation. Okay, so this is the equation. So we can write the equation first. We have dr dt equal to negative kr. R is the radium. If 10% decomposes in 200 years, what percentage of the original amount of radium will remain after 1000 years? So at first, when t equal to 0, your radium is 100%. So this is the initial amount. Okay, when the radium, the radioactive exploded, okay, so it emit 100% of the radioactive. So we state here as 100 or 100%. But if the initial amount of the radioactive is given, so you need to use that given amount. For this case, the amount is not given, so we can simply assume the initial amount is 100%. Okay, next, 10% decomposes in 200 years. Decomposes here means dia tu hilang. Okay. So, what is the remaining percentage? So, will be 90%. Okay, at first we have 100%. After 200 years, okay, it becomes 90% because 10% decomposed already. Okay, what percentage of the original amount remains after 1000 years? So we want to find the radium or the amount remains. Okay, so as previous example, first of all, we need to separate the variables. So we have 1 over r dr equal to negative k dt. By integrating both, so we will get ln r equal to negative kt plus c. And by taking exponent for both, we have r equal to exponent negative kt plus c. Or we can write as exponent negative kt times exponent c. And we state exponent c as a. Therefore, we have r equal to a exponent negative kt. Okay, so this is the general solution. Okay, and for the case when t equal to 0, or for the initial amount, so we substitute 100 equal to a exponent 0. Okay, t times negative k. When t is 0, everything becomes 0. Therefore, we will get a equal to 100. And then we can write r equal to 100 exponent negative kt. The next information is when t equal to 200, the amount becomes 90. So 90 equal to 100. Okay, we refer the previous equation. So we have r equal to 100 exponent negative kt. So for this case, for now r is 90. So 90 equal to 100 exponent negative k times 200. Your t now is 200. Okay, by rearranging the numbers here, so we have exponent negative 200k equal to 9 over 10, right? And then negative 200k is ln 9 over 10. Then k equal to, okay, so what is k? Negative 1 over 200 ln 9 over 10. Therefore, the equation becomes r equal to 100 exponent. We have negative k, negative kt. The value of k here is negative. Therefore, it becomes, okay, the equation becomes t over 200 ln 9 over 10. Now, we have negative k, and the formula is negative here, and it becomes positive. So 100 exponent t over 200 ln 9 over 10. Okay. Back to the question. We need to find the percentage remains after 1000 years. So when t is 1000, so we have r equal to 100 exponent 1000 over 200 ln 9 over 10. And you can use your calculator to get the answer, and we will get 59.049%. Okay. The third application is Newton's law of cooling. When an object has a temperature greater than the ambient temperature or surrounding temperature, ambient here means surrounding, okay, it cools according to Newton's law of cooling, which states that the rate of cooling is proportional to the difference in the temperature, meaning temperature of the object and the surrounding or ambient temperature. So we will get d theta over dt equal to negative k. Negative here because the temperature is decreasing. So this is the decreasing rate, and theta minus a is the difference between the two temperatures. Okay, where theta is the temperature of the object at any time t, and a is the ambient temperature. the solution to this separable differential equation, okay, will be, okay, so this is the formula according to the Newton's law of cooling. So now we will try to separate. So we have 1 over theta minus A, d theta equal to negative kt. And now we will integrate both sides. So we'll get ln theta minus A equal to negative kt plus c. And by taking exponent for both, we have theta minus A is exponent negative kt plus c, and we will get theta is A exponent negative kt plus A, where your capital A here is exponent c. Okay, now we go to the example. A pie is baked at 180 degrees Celsius is removed from an oven. Okay, so at first, okay, we have 180 degrees pie. Okay, we remove and we put into the kitchen. And the kitchen have the temperature of 70 degrees Celsius. Okay, so the pie is cooled off to 160 degrees after 5 minutes. Okay, so when T is 0, so this is the initial, the starting, we are using theta here. So theta is 180 degrees. Next, the pie is cooled off. After 5 minutes, the temperature becomes 160 degrees. Okay, given the equation here. Find the time taken for the pie to cool off to 135 degrees. So 135 degrees, what is the time? Yeah? Okay, so we go to the equation. We have d theta dt equal to negative k theta minus A. And for this case, what is A? Okay, what is A? What is the surrounding temperature? Okay, so awak tengok kat sini, with a constant temperature, the kitchen with a constant temperature of 70 degrees here. So this is your ambient temperature. And if you notice here, okay, the ambient temperature must be smaller than the temperature of the object. Nah? Okay, so we write d theta dt, we put the ambient temperature here, which is 70. Now we try to separate. We have d theta over theta minus 70 equal to negative k dt. And we integrate both sides. We will get ln theta minus 70 equal to negative kt plus c. Okay. And then theta minus 70 equal to exponent negative kt times exponent c. Theta is A exponent negative kt plus 70. Okay, so this is the general solution, right? Okay, the general equation. And now we go to the question. Okay, given when t is 5, the temperature is 160. So 160 is A exponent. Sorry, I skip when t is 0, isn't it? Okay, so sorry, we go back. So we check when t equal to 0 first. So when t equal to 0, the temperature is 180. So 180 is A exponent 0 plus 70. Exponent 0 is 1. Therefore, we will get A equal to 180 minus 70 is 110. Okay. Therefore, the equation becomes theta equal to 110 exponent negative kt plus 70. Okay, so this is the equation after we got the value of A. Okay, next information is when T equal to 5. When T equal to 5, the temperature is 160. 160 equal to, okay, we use the second general equation here. Okay, kita akan guna yang latest equation lah. So 160 equal to 110 exponent negative k times 5 plus 70. Okay, then we try to simplify. So we have 90 equal to 110 exponent negative 5k, and exponent negative 5k equal to 9 over 11. Therefore, negative 5k equal to, okay, now for this part, by taking ln for both sides, so we get ln 9 over 11. K is negative ln 9 over 11. Then divide by 5. Okay, so this is the value of K. Or if you try to calculate, okay, so you will get the answer is negative. So 0.0401. And then the equation becomes theta is 110 exponent. Okay, negative becomes positive. So we have negative, sorry, this is, we substitute k inside. We substitute k into the equation. And here becomes 110 exponent negative 0.0401 t plus 7t. Okay, so this is the final equation lah. Okay, after we got k and A. Okay, so back to the question. We want to find T, the time when the temperature is 135. Yeah, so we use the equation. So we substitute. This is the question, so 135 degrees. So 135 equal to 110 exponent negative 0.0401 t plus 70. We simplify. We have 65 equal to 110 exponent negative 0.0401 t. Next, exponent negative 0.0401 t equal to 65 over 110. Now you can use your calculator to get the answer lah. Okay, and by taking ln for both sides, so we will get T equal to 13.12. And for this question, we are using minutes. Okay, so we write minutes here. And the next application is electric circuit. Okay, so for this is a simple RL circuit, and the equation is di dt plus R over Li equal to E over L. Okay, and R related to inductance, L related to inductance, R the resistance, and This is according to Kirchhoff's second law. And we go directly to the question. Okay, the basic equation, okay, governing the amount of current I in a simple RL circuit given by the equation here. So we have di dt plus 50I equal to 5. When t 0, I is also 0. So at first, the current I is 0. Find the current at any time t. So IT in general. The question is I of t is what? Okay. So now we go to the given equation. So we have di dt. So di dt equal to 5 minus 50I. We try to separate the variables. So we have di over 5 minus 50I equal to dt. And we try to integrate both sides. We will get ln. Okay, we have ln here. 5 minus 50I. Don't forget to differentiate the inner function. So we have divide by negative 50. So we have negative 50 here. Equal to t plus c. Okay. Next, we have ln 5 minus 50I equal to negative 50t minus 50c. By taking exponent for both sides, we have 5 minus 50I equal to exponent negative 50t minus 50c. Or we can write exponent negative 50t times exponent negative 50c. Exponent is a number and c is also a number, a constant. So we can let this part as a. Okay. So we have 5 minus 50I equal to a exponent negative 50t. And then we state I as subject. Okay. So we have I equal to 5 minus a exponent negative 50t, then divide by 50. Okay, so this is the general solution. Okay, and next, given at the beginning, when t is 0, the current is also 0, isn't it? Okay, so we can substitute here. T0, current 0, I0. Therefore, we have 0 equal to 5 minus a exponent 0 divided by 50. And a will be 5. So we substitute again. Okay, so we have I is 5 minus 5 exponent negative 50t over 50. Or we can simplify and it becomes 5 over 50 is 1 over 10, right? So 1 over 10 times 1 minus exponent negative 50t. Okay, so this is the equation. And the last application for today is a problem related to velocity and acceleration. So this is more to physics quantity, right? So we go to example directly here. Example number 10. An object move from rest. Okay, the word rest here means the starting is 0. Okay, in a straight line, so that the acceleration, okay, acceleration in general we write as a, and acceleration is related to the velocity, isn't it? So A is dv dt. Okay, the rate of change of the velocity. Okay, so we write the equation here. dv dt. Okay, given acceleration is 8 minus 2v. Okay, so A is 8 minus 2v. So we change to dv dt is 8 minus 2v. Okay, and then we separate the variable. We have dv over 8 minus 2v is dt. And next, as usual, okay, we try to integrate both sides. So we have ln 8 minus 2v. Don't forget, okay, we need to divide by negative 2 equal to t plus c. And ln 8 minus 2v equal to negative 2t minus 2c. By taking exponent, 8 minus 2v is exponent negative 2t minus 2c. As usual, we apply the rule of indices. So exponent negative 2t times exponent negative 2c. And this part, okay, exponent is a constant and c is also constant. So we can write this part as a. So 8 minus 2v equal to a exponent negative 2t. And by rearranging the equation, we have v equal to 8 minus divided by 2. So 4 minus a over 2 exponent negative 2t. Okay, back to the question. Given when t is 0, okay, the word rest here, okay, from rest here, meaning that at first everything is 0. Acceleration 0, time 0, and velocity is also 0. So when t is 0, v is also 0. So we substitute into the equation. So we have 0 is 4 minus a over 2 exponent 0. Therefore, we will get a equal to 8. And the equation becomes v equal to 4 minus, okay, a is 8, 8 over 2 is 4. 4 exponent negative 2t. Okay, so this is the equation for the velocity. Okay, next one is estimate the value of v after a long time. The word long time here meaning that your t is approaches infinity, a very long time. So we have v is 4 minus 4 exponent negative 2t. Okay, if you try to recall the function here, the exponent function here, exponent negative 2t, okay, the graph of exponent negative 2t is like this. Okay, like this. So this is your x, this is your y. And the intersection is at y equal to 1. So when you move, okay, to the right here, or when t is approaching infinity, your function or your graph here will approaching 0. So when t approaches infinity, exponent negative 2t approaches 0. So now your v equal to 4 minus 4 times 0. So this is for the case of a very long time. And your V equal to 4. We are using meter and then second meter per second. Okay. And the last one. Show that the distance traveled after 2 seconds is 6.0366 meter. Okay. We know that V equal to 4 minus 4 exponent negative 2t. And V is ds dt. So ds dt is 4 minus 4 exponent negative 2t. Okay, the distance here referred to your s here. Okay, so we have ds equal to 4 minus 4 exponent negative 2t. So the target here is to find s. But if you go back to the question, you're asked to find the distance after 2 seconds. Right? Okay, meaning that we need to integrate, okay, from 0 until 2. Okay, integrate 0 until 2. Okay, so s equal to 4t. Negative will be plus divide. So plus 2 exponent negative 2t from 0 until 2. And we substitute. So we have 4 times 2 plus 2 exponent negative 2 times 2. And then minus 4 times 0 plus 2 exponent 0. And we will get equal to 6.0366 meters. Okay, that's all for this chapter.